So hi everybody, welcome to Organ Technology Part 8. In this series we're exploring primarily all the various circuits that go into building an analog technology organ. So think of Rogers from the 1980s earlier and all of those home organs that you saw as a kid in grandma's living room and all of that kind of stuff. So Thomas, Kahn, all of those kinds of instruments all worked on similar principles, and basically it's analog synthesis. Now, in past episodes, we've talked about oscillators generating a tone. We've taken a look at various filter schemes and tone generator schemes from individual oscillators right up to, single oscillator, divider network kind of stuff. And it's been a very interesting exploration. I wanted to get a little more into detail, and today we're going to take a look at the effect that capacitors have as a filter device in shaping the tone of an organ. Now, the goal has always been, well, first let's talk about where I'm seated here. This is my piano teaching setup. I have my, keyboard here that can be plugged into software to generate a piano tone, and an overhead camera so that my students can see what I'm doing. And then I have this other camera on my face. So I'm going to use this setup today to show you, draw some pictures schematics like I like to do on this show. But first let's talk about, what is a capacitor? Okay, well, capacitors are a device that actually does not conduct electricity. It consists of two plates and an insulating material in between them with leads coming off of either plate. So what happens is when current is run into the capacitor, it develops a static charge. When that current flow stops, then the capacitor discharges that static charge in the opposite direction. So if I have a static charge coming in here, then it's going to discharge when the current flow goes in the other direction. So obviously this works with alternating current or pulse current signals. So why two plates? Well, the belief has been that one plate is positive and one plate is negative. So depending on the current flow, one plate will develop a excess of electrons while the other plate develops a depletion of electrons. And then once you run the current in the other direction, that depletion zone is sucking the electrons off of the excess zone, as it were. That's based on the idea that electric flow is actually electrons flowing from one atom to the next in a wire. Turns out that maybe that's not exactly what's going on. Well, I don't know anything about that. We have to talk to the engineer types and the scientist types about that kind of thing. I'm going to include a video from a YouTube channel called The Engineering Mindset that's all about capacitors and shows in great detail how capacitors work and talks a little bit about the electrical theory that goes into that. But let's just suffice it to say that for tinkerers like me and maybe you, knowing that a capacitor works with certain characteristics, well, that's all I really need to know. And I'm always looking at schematics and maybe making modifications to build little fun projects. And that's really what our discussion is going to be about. And, this is for the tinker crowd, not the engineer crowd. But now the circuits we're going to take a look at today come out of this old Radio Shack book. I think I have a complete set of these. I'm not sure. Radio Shack is trying to make a little bit of a comeback, and they issued, and I'd kind of like to get it, kind of a compilation of all of the various basic circuit books that Forrest M. Mims put together. These are fun, and I've done a number of projects with this. I've created things for my model train layout, relay switch, solid state relay switching, and all kinds of fun little projects that can be done with really basic components. So if you find a set of these somewhere or want to buy the new reissue big thick book that has a bunch more stuff in it, these are really cool. I, of course, am going to redraw the circuits because, well, I don't want to get into any copyright issues with just flat showing you technically copyrighted material on here. But these are a lot of fun. These books also share with you a lot of really basic information that's very useful. How to make basic mathematical calculations with various components, and basic information on how they work and all that good stuff. Basically, at the end of the day, this charges and discharges, and that can be used for a number of different effects. Now, depending on the size of the capacitor, measured in usually microfarads, that charge and discharge is going to take place at a given frequency. So these really only work with pulse or alternating current. And so one of the really key things that we can do, simple things that we can do, which you've probably noticed on most speaker systems, you have a crossover network. And so a two-way crossover would consist of a capacitor that will only operate above a certain frequency. Let's say our cutoff point is going to be 500 hertz. So we get a capacitor that will only operate above 500 hertz. Well, at that 500 hertz point, the capacitor is going to be, it's not going to just stop, it's going to kind of taper off. So everything above 500 hertz and a little bit below 500 hertz is going to be let through. So we call this a high pass filter. Now you can use another device called an inductor, and its symbol is L, and it will only work below a certain frequency. So we get an inductor that's going to operate, we'll talk about inductors in another video. So we get ourselves an inductor that will only operate below 500 hertz. And again, there's going to be an overlap zone because it doesn't just stop, it falls away. So here we have our simple two-way crossover for a simple speaker system, so that only the low frequencies are going to the woofer and only the high frequencies are going to the tweeter. You get a cleaner sound that way. Okay, so most simple oscillators are going to generate a square wave. Now, this is only useful for certain types of tones. By itself, it sort of gives you a clarinet sound, but, we might want it to be a little different. We might want a different wave shape in order to generate, say, a flute or a diapason tone or a string tone. So there's a circuit called an integrator, and we have a resistor and a capacitor that creates a drain to ground. And then we have our output here. What happens here is that as the square wave is coming in, the capacitor is first generating a drain and then generating an output. So when the square wave goes high, this creates a delay effect on that rise. When the square wave goes low, this creates a drain that slows down, or a discharge that slows down that drain. And what we end up with is a triangle wave. Now, the difference between these two waves in terms of tone quality is very little. In fact, most people can hardly tell the difference between a triangle wave and a square wave. So triangle wave by itself is not all that useful, but we'll see in a moment how it can be used to create something even better. Alright, so now, that was an integrator. There's also a circuit called a differentiator. And again, we have our square wave coming in. And now we're going to arrange the circuit just in the reverse. We're going to put our capacitor here, And our resistor is going to be the drain to ground. And then we're going to have our output here. Okay, now what happens here? Well, this offsets the capacitor or the square wave's signal by 90 degrees, because while the square wave is high, the capacitor is charging, so nothing is happening over here. When the capacitor goes low, then when the square wave goes low, the capacitor then discharges. But some of that discharge is being drained off, and so the effect is that in an offset of 90 degrees in terms of the phase, so when this is going low, this goes high, but it tends to just jump to high because the capacitor has started to discharge. The drain to ground is affecting that discharge by slowing it down, and now we get a sawtooth wave. And a sawtooth wave is very useful for certain organ tones like strings or smaller diapasons like Gem's horns, that kind of thing. Now, we showed how with an integrator circuit we can convert a square wave into a triangle wave, but I also explained that a triangle wave is not the most useful thing. But there's another circuit, this time, that uses diodes to create a sine wave. So in this circuit, we have our triangle wave. We then have, the triangle wave is assumed to be bipolar. So this is our positive side, this is our negative side, and there's a 0 point halfway through. We then have a bipolar circuit, have our resistor, and then we have two diodes going in opposite directions. And that goes to the other side of our output, our bipolar output. Now, what we get here is a sine wave off of a triangle wave. Now, like I explained last time when we were talking about diode switching circuits and how they work with oscillator outputs, some of this is hard to visualize. But let's think it through. How does a diode work? And I'll put a video link to diodes. Diodes have a barrier voltage. You have to exceed a certain point before you can get through that barrier voltage. It's usually 0.7 volts. So in this case, we're taking advantage of that barrier voltage and how it impedes the progress of our triangle wave. And effectively, what is happening here, so we've got our triangle wave coming along, and we're clipping these peaks in a curve. And so since we've cut these points off through the effect of the barrier voltage in the diodes, now we've created an approximate sine wave. Now you'll also notice that the amplitude of the sine wave is indicated as being much lower than our triangle wave. And again, that barrier voltage is creating that effect. So as you can see by this, the charging and discharging of capacitors can be used in a number of ways. The other characteristic, the fact that the capacitor will only operate above a certain frequency range, that gives us an additional effect that we can take advantage of in filtering. And when we look at filters for synthesis, you have your oscillator, and like a Moog or a Korg synthesizer, you've got an oscillator generating a tone source, and then you'll have a filter that is a adjustable low pass, high pass, or band pass. And basically what those do is you affect how much of the low frequency is going through, how much of the, and how wide the middle frequency is, and how much of the high frequency is, and at what point does it go high, and all of those kinds of things. These are done, the exact same thing is done in an analog organ. You have your tone source, and then your filters are used to do what is necessary to shape that sound into the various tones that we need. So the typical thing in most of those old analog organs was that your tone generator is generating a square wave. You're going to use a circuit to reshape that waveform from square to sawtooth to triangle to sine to half sine. And all of those wave shapes give you the basic differentiation of sounds that you need. And then you can shape them further by using the capacitor and the inductor as high pass and low pass or notch filters to tune that wave shape into the tonality that you ultimately want to have. Now, in simpler organs, you had a single oscillator, a divider network to generate all of your pitches, and then you combined and divided and did all this stuff to create the various tones that you want. In more sophisticated organs, you would have individual oscillators, and then each note would go through different filter circuits to give you the different sounds that you wanted, tuned specifically to that note. So, again, I'm putting a couple of videos from the engineering mindset in the links in the description of this video, and I hope this has been informative and fun and helps you in your tinkering with old electronic organs. We'll see you next time.